Hello, this is lecture 15, and in this lecture we are discussing Kennedy's theorem, which is very relevant to the topic we started last lecture when we discussed the velocity pole and the rigid body motion in a plane. So, in Kennedy's theorem says first it says in the linkage, maybe you can say this item one, in a linkage, every two links share a point of common velocity. So that's like that every two links share a point of common velocity. And that's, well, obvious, like in a four-bar chain, such as this one here, right? I have links here, I have link 1, link 2, link 3, link number 4, and I know this point is the velocity pole of link number 2. So the velocity of this point is actually 0. Okay, so this means, and also don't forget the ground has a 0 velocity. So this point falls on link number 2 and also in the ground because it has a 0 velocity, which is common between the two links. So this point here, I can call this point, I can say it's point 1, 2. So it's, and so that's one of the obvious points. Another obvious point here is this point. This point is common between link number 1 and link number 4. It has a 0 velocity. It's the velocity pole of link number 4. Okay, and because the velocity of the point is 0, it must be actually falling. It must be on link number 1 because link number 1 has 0 velocity. So it's actually 1 and 4 together. So that's obvious. I have like here link number 1 and link number 4 have a point of common velocity. Link number 1, link number 2, they have a point of common velocity. Also, this point here, we referred to this point as point A previously. I can say this point is common between 2 and 3. I can say 2, 3, right on top of the point 2, 3. Just to remind myself, that's common between those two links. And this point is common between 3 and 4. So I can write 3, 4. All right. So I found now points common between 3, 4, right? I have in this linkage, I have 1, 2, 3, 4. The theory says every two links share a point of common velocity. So I found 1, 2. This was good. I found 3, 4. This was easy. Just comment here. I found 3, 2, which was this point here. That's simple, right? I found 1, 4. Okay. And as still some of them are not easy to find. For example, how about 2 and 4? They must share a point of common velocity because the theory tells me this is the case. How about 1? Maybe change the color. How about 1 and 3? They also must have a point of common velocity, which you'll discover now we have done it before. 1, 3. Okay. In any case, the theory says this is the second item of the theory, which says the 3 points shared among 3 links, right? The 3 points of common velocity shared among 3 links are collinear. They fall on the one straight line. So 3 points shared among 3 links are collinear. Right. How does this apply? So, for example, I have here links 1, 2, 3. All right. So they have 3 points. There is 1, 2, there is 2, 3, there is a third point, which is 1, 3. And you realize that 1, 3 in my example here, this was 1, 2. That's 1, 2. And here, this was 2, 3 over here. And the missing point is 1, 3, right? Okay. Now, so 1, 3 must fall on the line which connects 1, 2 and 2, 3. So normally when I apply this second part of the theory, I would always have 2 points. Look for any 2 points with a number, with a common number between them. So that have 1, 2, 2, 3. That's 2 is common. So the missing point is 1, 3. And try to find 1, 3 by saying it must fall on the line which connects the 2 points. So now if I extend this line here, right, I know that point 1, 3 must fall on this line. So 1, 3 must fall on the line. I don't know where exactly it will fall on the line, but it must fall on the line. And so hence I can put a sign on the line. I can say this is a locus for 1, 3. So I like to put an L like that for the word locus, meaning that 1, 3 has to fall on this specific line. All right. I can also find 1, 3. If I want to find point 1, 3, I have to find another line, another locus, and then find the intersection of the two loci. So I can, if I come from the other end to the linkage, I have 2 points here. This point 1, 4, point 3, 4. The number, common number here is number 4. So the missing point is 1, 3 again. So this, if I extend this line here, should give me point 1, 3 from another locus for point 1, 3. So this here will be locus for 1, 3. So now I have two lines representing 1, 3, and as the lines intersect over here, this must be point 1, 3. So I have found my point 1, 3. Now, remember in the last lecture, we also did find the point 1, 3 by drawing perpendicular, like the velocity at this end, right? We call point A, which and draw perpendicular to the velocity VA, and then we did the velocity at the other end, VB, and we did perpendicular to that, and then we extended the two perpendiculars till they intersected. We found the pole of link number 3, which is exactly point 1, 3, because it's common between 3 and 1 whose velocity is 0, and the velocity of this point is actually it's 0. So this is pole in instantaneous center, or whatever you want to call it. So this sort of thing, that's 1, 3. Okay, similar to 1, 2 and 1, 4, they are both instantaneous centers. The difference is because 2 and 4 do only rotation, but link number 3 does general motion, so its pole actually changes position in the plane as we discussed before, and the path of point 1, 3 on the plane is a fixed trajectory centroid, and if you draw the same path on the moving link 3, you'll get a moving centroid as we discussed before. So how about point 2, 4? So there is a missing point here, 2, 4. I still have not actually found. 2, 4 also, I think about 2, 4 in the same way. So I have over here, I have this here is 1, 4. This is 1, 2. Common number between them is 1. The missing number is 2, 4, right? So this is a missing point. So what I can do is just extend this line here, and I know this will be a locus for 2, 4, right? Okay, and now I need to find another locus for 2, 4. If I just extend here, this is point 3, 4 and point 2, 3. Common number here is 3, so the missing point is 2, 4. So when I extend that, I get another locus for 2, 4. So this is a locus for 2, 4. That's another locus for 2, 4 with the intersect. This is point 2, 4. So this way I have found all the points of common velocity in a linkage, if you like. You find that, well, box would tell us the number of common velocities point is n minus 1 over 2. There's some equation, something like that, which tells you this will be the number in a linkage of 4. So n is equal to 4. So that's 4 times 3 over 2 is like 6 points or something like that. So I should be able to find 6 points of common velocity, and we found 4 on these edges and 2, 1 here and 1 there, so that's 6 points. And you find in some textbooks people use they draw like a circle on the side and they put points like number links here, like every point represents one link, and try to connect, make sure every 2 points are connected, and when they make sure every 2 points are connected, they know they have got all the points of common velocity in the linkage. That's one way of just trying to work in a systematic fashion more than anything. All right, I'm going to do this one example one more time and just try to maybe just talk about the velocity next time around. So over here, this is my example again, just repeating the example one more time. Okay, so here I have here. So this is link number 2. Maybe you can just reduce the length a bit over here. So over here, that's link number 2, right? So number 3, all right? So that's here, ground. So this is link number 2. So I put 2 with a circle. Link number 3, 3 with a circle, 4, circle, 1. I put 1, put a circle around it, and then I find my points. I know my point here. This is link number 2. Okay, so I have this is common between 1 and 2, so I put 1, 2 on it, and this is 1, 4. I put 1, 4 on it. This is a fixed like poles for those links, and this here is 0.34, and this one is 0.24. That 2, 3. Sorry, that's common between 2 and 3. Now, if I want to find like 1, 3. I realize from this end I have 3, 4. I have 1, 4. Common number is 4. The missing point is 1, 3. So I extend this link here. I know that's a locus for 1, 3. And at the other end, I know this 1, 2, 2, 3. Common number is 2. The missing number point is 1, 3. So I extend this other link here, and this will give me 1, 3. All right, okay. So at this point, if I why I'm doing that, this is the question. Because normally, in fact, people do this as a graphical way of doing your velocity analysis instead of equations, right? But the way they use it is like that. Now I have normally I know the velocity of my input link, like this is omega 2, right? So I know the velocity VA or V whatever, if this point A, I know VA, which is VA is equal to omega 2 R2, correct? Okay, now this is VA. A is common between 2 and 3. So A falls also in link number 3. That's why it's between, we put 2, 3 on it. Okay, so I know now a velocity of a point on link number 3, and I know link number 3 instantaneously at this point in time is fixed at this around this pole. So straight away I can tell, I can also calculate this point because it is on link number 3. I can write it's equal to omega 3 times all this distance. Let's call it h3 or something. All this distance like from here to there. Because at this point in time, link number 3, as if this link here, as if it is just doing pure rotation about 0.13, and I can calculate any point velocity of any point on it by connecting the point to the pole and then multiply the distance by omega, and will give me even the direction and the value of the velocity. So I can say on the side here, I can say omega 3 h3 is equal to omega 2 r2, and this gives me an equation for omega 3 at this specific point in time. So that's not an expression I can substitute at any value of whatever, because what happens here is the value H3 is going to change as the linkage rotates, and then you get a different value for omega 3. All right, this is as simple as that. Now, also, same thing, omega, if I wanted omega 4, at this point in time, by the way, I can find my omega 4 because now I know the velocity of link 3. So if I draw a link 3 rotates about 1, 3 over here. So now if I draw perpendicular over here, this will be omega 3 L3. So I can, let's call all this distance L3, right? But also this point is common between 3 and 4, so it does fall on link number 4, whose fixed centroid, a fixed pole is 1, 4. So I can say also it's equal to omega 4 R4. And this way I can find an expression for omega 4. So omega 4 R4 is equal to omega 3 L3, and I can calculate omega 4 as being L3 over R4 omega 3, this sort of thing. So I can get the velocity of omega 2. So my input to the information, this is the input information here. I mean, input to solution, that's input. And I want to calculate two outputs, two velocities. I calculate this as an output and omega 4 as an output. All right, I didn't even have to find 0.24. Okay, this sort of thing. So now it's how about if I do another example for you? So if I do this example here, that's point A, this is link number 2, and let's try, this is link number 3, and this is link number 4. Let's try to find the point of common velocity. And there are the ones that are easy to find, the quick ones, such as 1, 2 here, because this is common between 1 and 2, correct? And this one also, this is the easy to find because it's common between 2 and 3. So I put 2, 3 on it. And the pivot, this other pivot, every pivot is very easy. When I see a pivot, I know there is a common velocity at the pivot. This pivot here links link number 3 and link number 4 together. So this here represents 0.14. This pivot here is 1, 4. Okay, so I have 1, 4. Why? How about 2, 4? I must have 2, 4. Okay. No, that's this point. In fact, no, this is an error. I should say this is about links number 3 and link number 4. The pivot represents links number 3 and link number 4, right? Not 1, 4 at all. In fact, 1, 4 is something we need to think about. So this pivot links 3 and 4. So I should say 3, 4. If you want to call it 4, 3, that's absolutely okay as well. It doesn't matter which one you mentioned first. Okay, so how about 1, 4? Right, 4 in fact slides on 1. Remember the pole for the sliding link? It fell last time we discussed it, was actually perpendicular to the direction of sliding at infinity. So 0.14 as in this direction, it's actually going at infinity, right? Sort of thing. This is 1, 4. So this specific line then it will be a locus for which point? If this is 3, 4, and this is 1, 4, you see the common number is 4. The missing point is 1, 3. So this has to be a locus for 1, 3. So this is like the pole of link number 3 should fall on this line. What is the other? I need to find another locus for 1, 3. So I can come to the problem from the other end, and I can say, okay, this is point 1, 2, and this point 2, 3. Common number is 2. Missing point is 1, 3. And I can draw a line just along this here. and this will give me another locus for this, another locus for 1, 4, 1, 3. Okay, so the two loci intersect at a point, and this point is going to be the 1, 3 we're looking for. So this is 1, 3, meaning that this is the pole of link number 3, pole of 3, this one here. And we did actually look at this before also last time, because remember to find the pole of a general link. So we draw again like at velocity at both ends, this here, and this velocity here is perpendicular like that. This is VA perpendicular to 2, and this is VB, which was the sliding velocity, and you draw two perpendicular lines, two lines perpendicular to the velocity vectors, and those lines intersect at a point as we discussed before. This will be the velocity pole. So this is how we got it before, but this time around we are getting the same point using Kennedy's theorem, which says that every three links share 3 points of common velocity, and these points are collinear. So on this line here we are talking about the 3 points, which is 1, 4, 3, 4, and 1, 3. They are shared among 1, 4, and 3. And this line here, we are talking about 3 points, 2, 3, 2, 3, 1, 2, and 1, 3. And they are common among 2, 3, 2, 3, and 1s. Those points. So sort of thing. Okay. How about 2 and 4? Do they share a point of common velocity, 2 and 4? This is link number 2, which is a crank, and this is link number 4, which is the slider. How to get point 2, 4? I want you to think about this for a second. Point 2, 4. Okay. Now, which direction will it be on? Well, like which, let's find a locus, right? So, okay, if I look at this side here, I have this here is 3, 4, and this here is 3, 2. So the common number is 3. So the missing point is 2, 4. So this line which is link number 3 itself is a locus for 2, 4 on the link, the point line which connects A and B at this end. This line is a locus for 2, 4. I need another locus for 2, 4. Okay, anything like, if any thoughts about this? Okay, now what if we have, you see, if this 1, 4 at infinity and 1, 2 here, which is a pivot of link number 2, so the common number is 1, the missing point was 2, 4. So I need to connect this point to this point at infinity, and this will give me a locus for 2, 4, correct? Now, but how do I draw a line here to intersect this vertical line at infinity, right? The only way for to intersect lines at infinity, to intersect two lines at infinity, is to draw them parallel to each other. So you have to draw here from 1, 2 parallel to 1, this 1, 4 at infinity, and those two lines will intersect at infinity. And then this will give you a locus for 2, 4, another locus for 2, 4, meaning that this point over here is going to be 0.24. So this is 0.24. So now I found 6 points. If you are given the velocity of 2, like omega 2 is given, and you need to find your unknowns. Your unknowns are v velocity of the slider B. Your unknowns, another unknown is omega 3. Those you need to find these values. This is when you conduct those velocity analysis, you need to find that same. And this is just a graphical way of doing velocity analysis. So when I have my omega 2, this means I have VA, which is omega 2 R2. So this is my input to the process. Okay, and I can straight away say that point A falls also on link number 3. This is this pivot here, that's common. So I can find the velocity of this point being on 3, and 3 rotates about this point here at the bottom, which is 1, 3. So if I multiply omega 3 by all this distance here, right, this will give me the velocity of this point as well. So V, which is also omega 3, let's call the distance h3, for example. So now I can write this expression which says omega 3 h3 is equal to omega 2 h2, and sorry, omega 2 r2, I should say, omega 2 r2, and I can get from this expression omega 3. Now, how about velocity of the slider VB? I need to get VB at this point in time, having calculated omega 3. Okay, I can get it two different ways if I want to. I can from this end here. I know now omega 3 because I just worked out omega 3. And if I want to calculate velocity of point B, this point, which falls on link 3, don't forget the slider, the pivot connects the slider to link 3 over here. So because this VB falls on link 3, I mean point B falls on link 3, I can say its velocity is equal to omega 3 times h3, where h3 is all this distance over here. That's no, L3, call it L3. I call the other side H3. I'm going to call this one L3. So, right, that's L3. So now VB is equal to L3, omega 3, L3 will give me the velocity of point B, which is actually just a slider. So now VB is omega 3, L3, and this is what I wanted to get. That's one way of getting the velocity of the slider. If you want to think of another way, the other possibility, if you say, okay, this point is 2, 4, which here, right? 2, 4 falls on link 2 and link 4 in the same time. So its velocity being on link 2 is equal to omega 2 times this distance here. Let's call it h2, right? So this velocity here is equal to omega 2 h2. But also it falls on link 4, and link 4 is just point B, the slider. So this is VB. So you can say another way of getting VB is equal to omega 2 times this distance, because this point is 4, 2 falls on link number 2. So it's omega 2 h2. This sort of thing. All right. So what if I decided to draw this specific example in a different configuration, so a different position? Let's say that I have this situation here, like one of those, like the link number 3 is at what I call its extreme position, like in terms of angle, or this is angle as far as high as it can get in terms of angle. But still, we discussed it last time. Link number 3, even though stopped, it's not rotating at this point, but will still translating with some velocity type thing. Let's see if we can use this method to find what's happening, right? And find omega 3 and whatever, which should be 0. Let's see what will happen. Okay, so now I have here, this is link number 2, link 3, and link number 4. This point here, as before, is point number 3, 4. And this point is 2, 3. And this point is 1, 3, the obvious ones. I know to get common between 4 and 1, I draw perpendicular like that. So this will be 4, 1 at infinity, because 4 slides on 1. So that's just as a pivot. Okay. Now, and this is perpendicular as well, right? So this is the thing I'm drawing here. This is R2, that's perpendicular. So now if I want to find 1, 3, so this will be locus for 1, 3, because I have the two numbers. I have 1, 4 at infinity. I have 3, 4 here, the common, so that's 1, 4 and 3, 4, right? And the missing number, the common number is 4. The missing point is 1, 3. So this is locus for 1, 3. Same thing at the other end of the linkage, where I have 1, 4. I have 1, 3. I have 2, 3. So the missing number is 1. Sorry, this here should be 1, 2, shouldn't it? Because it's link number 2, and the frame which is link number 1. So this is 1, 2, and this is 2, 3. So 2 is common between this one and that one. The missing number is 1, 3. So I draw, extend this one to say this is locus for 1, 3. So I have now two loci for 1, 3. I have this one and this one. But they are parallel to each other because this side here, the blue one, is perpendicular to the frame, and this other side next to R2 is also perpendicular to the frame. So this means those two lines intersect at infinity. So this means 1, 3 is actually at infinity. This means link number 3, in fact, slides at this point in time. Link 3 slides on 1. So exactly like a slider, exactly like link 2. So if the link slides, there's pure translation. Remember, that's pure. I just want translation, just only translates. This means omega 3 is equal to 0. And not only that, I can get, when a link is just doing pure translation, I can get velocity of any point on it, and this will be the velocity of any point on the link. All points have the same velocity in the same direction. So if I get the velocity of this point A is equal to omega 2 R2, right? And that's every point on link 3 will have the same velocity, including the slider at the bottom end. They all have the same velocity. So this means VB is equal to omega 2 R2. At this point in time, just the velocity from this end here goes through to this end here. So all this together, 3 and 4, at this point in time when 3 is doing the maximum angle it can do, 3 and 4 slide together. That's one of the singular situations we may deal with. Now, I also want to say that, so now the cases I looked at, they all have sort of, if you like, uh, lower pairs type thing. So, and it's you have with cases lower pairs like this, those cases, obvious you have like such as this one. That's all revolute and prismatic joints and this sort of stuff, lower pairs. So you can find some quick points like that, which are just when at the pivots, when you have pivots, and then you can link them together to find the tricky points type thing. But the interesting bit, if you have like higher pair type thing, so because higher pairs don't link up like in this case with pivot, like with pivoted together type thing. They are more like half joints. You can separate them if you like. So the higher pair is some interesting thing to higher pairs. The question is, where is the point of common velocity? This is the question we want to answer. So with higher pairs, we have two types of, or if you like, two types of contact. So higher pair, really, it's more like contact type thing. When higher pair, we talk about contact. The buzzword is contact more than anything. So we have two types of contact. We have the rolling contact, and we have the sliding contact. And most situations are maybe cases between both. Rolling contact won't use if you use rollers, like okay, but there is a condition for a contact to be or like rolling contact, right? Sort of thing. Rollers in terms of cams, because we are going to see. I'm just writing this here, not very like accurate, but I'm saying because we are going to see rollers, we're going to see cams together. So if we have a roller, I straight away think of rolling contact, right? Okay, the rounded thing just manufactured in this way to produce rolling contact. Rolling contact scientifically really defined as what? If we have 2 points, if we have two links, two bodies, whatever, and like in contact like that, okay. And if the point of contact, if it has the same velocity, so if the velocity of the point of contact is common from either link, the same on either link, this is rolling contact, right? So the point, so rolling contact, right? So the point of contact is the point of common velocity. Point of contact is the point of common velocity. That's rolling contact for you, right? So if I can say that's here rolling contact because I extend, you see this link here, say this is link 2 and this is link 3, one being the frame, then this point I refer to this point as 1 2, this point is 1 3, right? So if I link the 2 points like that, they go by the point of contact. Now, you know, every link of those is doing pure rotation, right? So doing rotation. So if you want to get the velocity of this point being on link number 2, it will be perpendicular to this line. Being on link number 3 will be perpendicular to this line. So it's really the same, which is the same line which connects the two like two poles, if you like. So it is, you can say the velocity here would be the same, and you can say that's rolling contact. So you can write the equation here saying if this was R2 and this was R3, you can say omega 2 R2 is equal to omega 3 R3. Rolling contact makes things much easier for us, such as this one, right? Now, the other situation, if the links are like that, so maybe just may give myself some room, just delete this here and give myself a little bit more room. So if I have a situation such as this one, right, the contact here, and that's here, and this is fixed here. Now you can tell if I plot, if I find where the point of contact is, and I connect those together, and I connect those together, type thing, then the velocity is not the same because the velocity on link number 2 is perpendicular to this line, right? So this is VA being on 2. Let's call the point of contact A, right? Being on the other link, I'm going to give it a different color. So being on this other link here, I'm going to say, okay, go back to this. So this is here the point which goes to that, okay? This is the line which goes to the pivot. All right. So this line here from the point of contact to this second pole. So this is point 1 2, this is point 1 3, this link number 3, and the velocity, let's say, is something like that. VA being in 3. So the point of contact has two different velocities, right? And so on each link there is, it's not the same velocity because everyone, the way the contact is made, like it's all based on geometry more than anything. And in this case, I don't have rolling, that's not rolling contact, right? So you can say sliding contact. It's really a combination of rolling and sliding. So that's more a combination of rolling and sliding, and that's more of the like higher pair can be combination of rolling and sliding. So sliding plus rolling like that. So type thing. So in this case, what happens? Where is the point of common velocity then? You ask. Okay, the point of common velocity, I cannot find it straight away. What to find it, I need to draw a line which is common, which is perpendicular to the tangent. Perpendicular to the tangent. So I come to the point where I have the two curves. So draw tangent, right? And then perpendicular to the tangent. And this will give you where the point of common velocity is going to fall. So this is tangent, and this is perpendicular to tangent, right? This is perpendicular to tangent. So this will be locus 4.23. That's as simple as that. Okay, now let me just quickly remind you that for rolling contact, the point of common velocity was the point of contact, the point of contact itself. This is the point of common velocity. So I should call this point 23 here, right? Whilst if this was other other type of contact, it's not, I'm not 100% certain it's rolling. I have to draw a tangent and then perpendicular to the tangent, and then this will give me where the point of common velocity is going to fall. And in this case, of course, you can tell straight away if you want another locus for the point of common velocity. This example will be as simple as, you see, this applying Kennedy's theorem. This is 0.13 here. Okay, this is 13. Just clean it a bit. So this is 0.13, and this is 0.12. The common number is 1. The missing number is 1, is 2, 3. So I can just connect those together, and this will give me another locus for 2, 3. So when those two lines intersect, I'll get 2, 3. The intersection 2, 3 will fall at the intersection of these two lines. Okay, so it's still, it is also possible with this complex form of contact of higher pairs to find the point of common velocity, and we do find them. Okay, so don't worry about that. That's what we do. Always in the examples, you'll be able to find clues to find the point of common velocity type thing. So let's look at some example. Let's say I have a wheel, right? And I tell you the wheel is going on the ground at some velocity omega, and it's doing pure rolling. So that's pure rolling. This distance here is r. Find the velocity. Find velocity of point A. Find VA. All right. Okay. Now what you do is you say this is pure rolling. So that's, I'm going to call this an example. So that's pure rolling. And then I know pure rolling, the point of common velocity is the actual point of contact. Don't forget that. That's very important. So if the ground is link number 1 and this is link number 2, so this point here is 0.12. Okay, that's 0.12. So if this is 0.12, common between 1, 2, then what is the velocity of this point? It has to be 0. Anyone that's shared with 1, any velocity that's shared with link number 1 has a 0 velocity because link number 1 is stationary. Then this means straight away I can look at this wheel as being pivoted over here under pure rotation. So doing only pure rotation. At this instant in time, it's not like when I know the wheel will rotate and will bring another point in contact with the ground. And every time we'll have another point of contact, but every time this point of contact will be the point of common velocity, will be the zero velocity will be the pole of the wheel. So this is the pole of the wheel because it you know why? Because it has number 1 in the name. So this is the pole. So you can tell straight away that as the wheel moves, the fixed centroid, that you know the mark, that the pole that it lives on the ground or the stationary link is actually the straight line. So this is the fixed centroid. So this is the fixed centroid of the wheel. And the moving centroid is the wheel itself, because as it shifts to another point, so the point that was in contact before, right, it remains on the wheel and will become a point on the wheel type thing on the, like here, circumference. So you can tell this is a moving, the wheel itself is a moving centroid, and the ground is a fixed centroid. If you want to think about it in terms of centroids as we did last time type thing. So if I want the velocity of point A now, what I do, because I know the wheel is doing pure rolling instantaneously at 0.12, I can say just omega times the distance to the pole, omega r. This will give me the velocity of point A. If we do, let's do another example. So let's say I have a cam such as this one. So let's say I have a cam and right here. So okay, let's say that's cam. Just try to plot myself. Okay, so here I have a cam and I have, let's pivot it, let's say pivot here, and there is a follower, and the follower over here just there is like there is a roller connected here. Roller should be circular, of course, right? And then let's say it's something like that. And I want my points of contact over here. So now let's count our links and find points of contact. So I have the cam is link number 2. The roller is link number 3. The follower is link number 4. So I have 4 links. The ground is link number 1. So now if I wanted, that's an example, another example. So if I wanted, let's find the points of common velocity. This point here, this is easy to find one, which is 1, 2, common between 1, which is the ground, and 2, this is the pivot, which is the cam. That's 1, 2. Another one which is really easy to find is the pivot over here. This pivot is point 3, 4, common between 3 and 4. All my pivots are very easy to find. Also, once I have rolling contact, that's a bliss, because the point of contact, the actual point of contact, don't forget that's higher pair. Then the point of contact is, and that's a roller, so that's pure rolling. So point of contact is a point of common velocity. So I can say this is 0.23 here. Straight away, it simplifies things a fair bit. And now how about 1 and 4? 4 slides on 1, so it has to be 1, 4 has to be at infinity. That's 1, 4. So now, if I want to find the cam, let's say velocity of the cam omega 2 is given. Find the velocity of the follower. The follower moves with some velocity v, and I want to find the velocity v. So I mean, find the velocity of 4, right? Find v4. Okay, so let's see how to find the velocity of 4. So 4 moves up and down, as you know. Right, so I need to find maybe now a point which is common between 2 and 4, simply because 2 is a pure rotational case. So any point on it, if I know any point, I want a velocity of any point, I just connect to the pivot and say, call this whatever r or whatever omega. So velocity is r omega type thing. So as simple as that. This is the cam. Cam is like that. So if I find a point on it and it's 2, 4, for example, then I know I just do perpendicular to the line, and then this will give me velocity of 0.24. And if it's called 24, it falls on 2, so it will be on 4. So there's velocity of 4, which is the follower. This is the strategy I'm following. So now let's see how to get to 4. So now the straightforward one at the start, I have here, I have 0.12, and I can connect it to 1, 4 at infinity. So draw parallel to 1, 4. So now the two numbers, the common number is 1, the missing number, the missing point is 2, 4. So this will give me a locus for 2, 4, right? So 2, 4 should fall on this line. I need another locus for 2, 4. I can see it here on my roller. So the center of the roller is 3, 4, and the point of contact is 2, 4. So if I connect them together, I get another locus for 2, 4, because 3 is a common number. So if I connect them together like that, those two will give me another locus for 2, 4. So now I have two loci for 2, 4, this horizontal one and this one at an angle. They intersect at a point. This has to be my point 2, 4. So this falls on the cam, number 2, and on the follower up here, number 4. The common point is down here. So if I want the velocity of this point, I can call this R2, and I can say, okay, velocity here is equal to omega 2 R2. It is the same velocity of the follower because the point is called 2, 4. So it falls also on 4. So this is V of the follower. That's one example. Let's do another example. Let's do another example. So if I have a different kind of follower, so if I have the flat-faced follower, so a follower is something like that, and the cam is something like that here, and that's the point of contact, and the cam is pivoted here, whatever, and that's the follower. So let's say I know the cam has a velocity omega 2, and I want to find the velocity of the follower. So the missing, so find V of the follower. This is the missing. That's what I want to find. So now, again, let's count our links. And I have the cam is link number 2. That's link number 2. The follower is link number 3, and nothing between them. So I have 3 links because I have higher pair. So the links, remember the minimum number of links you can run in a planar thing is 3 if you don't have higher pairs. But since I have higher pairs, this higher pair here, then I have 3 links and will constitute a linkage without a problem. Okay, so now let's count our points one more time. Just try to clean this a bit, Smithy. So I'm going to say, okay, this here is number, this here is point number 1 and 2. That's correct. And of course, perpendicular, the follower slides up and down. So perpendicular to the direction of sliding is 1, 3, goes to infinity. Now, so again, I want to find point 2, 3. So that's my strategy because this point will be on 2. So I can find its velocity on 2 because I know omega 2. So I can multiply omega 2 times the distance from the pivot to the point. And then it will be on 3 automatically. This will give me this velocity of the slider. So I'm after point 2, 3 or 3, 2 if you like. Now, so now if this is point here, the pivot is point 1, 2. Infinity, I have point 1, 3. Common number is 1. So if I draw a line perpendicular to 1, 3 and to infinity, this will be the locus for 2, 3. So that's a locus. I need another locus for 2, 3. And I'll get it from the contact between 3 and 2. Now, this contact here, don't forget, it's not a rolling contact in any way. So the point of contact is not the point of common velocity. And that's a mistake, students. You do that, that's a big problem, right? So the point of contact to get it, in this case, what you do, let's go back and just remind you how we do it. You draw, it's really perpendicular to the tangent, correct? Okay, so perpendicular, like similar to perpendicular to direction of sliding. So now, so will be perpendicular to this specific line here, which tangent to the curve. So this here, at the point of contact, I draw the perpendicular, and this will give me a locus for 2 and 3. That's another locus for 2 and 3. Don't forget, that's 90 degrees. So where they intersect, this gives me my point 2, 3, which I am after. So if I take this distance here as R2, I want to call it R2, I can say then V23 is equal to R2 times omega 2, is omega 2, which is, that's the velocity of the slider, because slider of the follower, because follower is link number 3. You can do plenty of examples if you get for example, the position analysis tutorial has a number of examples. You can try to take those examples and do them, and just to just train yourself, use a method which comes quite handy with some situations. And sometimes we use, like we use we, sort of, we try to relate velocities together with mathematical expressions, and we turn the method into a mathematical outcome more than anything as well. That's a common thing we do also in practice. All right, let's see if I can insert one of the examples I have on here in my file. Okay, so that's possibly like an easy one. We did someone an example very similar to this one. Okay, okay, over here, like smaller, right? And then yes. Okay, so now this is if that's an example. Over here, let's say that's example. So this is link number 2, which is a cam, right? Link number 3 is the roller, and this is link number 4. And as you know, I just wanted to do this in front of you so you can see like a better drawn one. So over here, I have point of common velocity, which is this is the pivot, the center of the pivot is 1, 2. I have in any direction 1, 4, infinity. By the way, because this goes to infinity, you can draw it from anywhere. It does not matter at all, right? So you take parallel to it. Always you take parallel to it because we don't intersect it with anyone, right? So any line, you just need a parallel line. So like if I connect this to 1, 4 at infinity, I get a locus of 2, 4, as simple as that, okay, sort of thing. So it doesn't matter where you draw this one, okay. Now this point, that's rolling contact. This has to be 2 and 3, and the center here is 3 and 4, and when you connect them, you get another locus for line for 2, 4. That's locus for 2, 4, and this point here is actually point 2, 4. Falls on the cam link number 2, and also falls on link number 4 at the same time, type thing, because the theory says like every two links have like share a point of common velocity, and those the 3 points shared among three links are collinear, and you can see here like point 3, 4, 2, 3, 2, 4. They mention three links amongst them, link 2 and link 3 and link 4, and they are collinear type thing. So over here 1, 2 and 2, 4, and sort of thing, and also 1, 4. So they mention those three links 1, 4, and 2. Okay, so if you want, if omega 2 is given, you can simply just find the velocity of this link, which is this point v24 is equal to omega 2 times r if this distance is r, type thing. Okay, okay, let's see if I can get another example. All right, so insert an image. Let's see if I can have another example for you. Right, let's see if I can have this one here, for example. Okay, this one, drag it like that, then info flattening. Okay, so this here is another example. So the points I have, this point here is 1, 2, okay, and this point here, this pivot, this time around I still have a roller follower, right? That's roller follower also, except the follower rotates or oscillates as opposed to translates. So not a translating follower, it's the rotating follower. So okay, so this follower here rotates, and it does pure rotation, if you remember, like as opposed to another follower like this one, which does pure translation. It's like sliding, pure sliding, and this one rotates, and this is a pole of this follower, so it's 0.14. This one here is 0.14, and this is the pivot, which is shared between 3 and 4. So this is 0.34 here. That's 3, 4, and because it's rolling contact, can change the color a bit and say this here is 0.23. That's 2, 3. So if I connect those together with a line, this line here, this will be locus for 2, 4, right? 2, 3, and 3, 4. There is a shared number which is 3. The missing point is 2, 4 will fall on here. Also, this is 0.12 and this is 1, 4. The missing number is 2, 4. So this will be this here is locus for 2, 4, and I know this will be my 0.24 now. So this is 0.24. So it does fall on the cam, but it does also fall on the follower. Okay. Now I mean, not physically, but I mean in terms of kinematics. Okay, so you can find the velocity of this point by saying, okay, now that's over here. Draw a line perpendicular to this line that connects. So that's this 90 degrees, and you can say this velocity here is equal to omega 2 r2, but also it is equal to omega 4 omega 4, let's say L4. L4 is the distance from here to there, from the pole of link number 4 to the point. This is L4. And this way, the missing information will be L omega 4, which I'm trying to find. So normally, omega 2 would be given. And R2, by the way, is this distance, little distance here. That's R2, right? Okay, so it's as simple as that. That's what you do. Maybe just we'll do one last example to finish those set of topics together. Just insert one extra page. Okay, so insert one extra page, page 70 or something, and then insert over here an example. And so let's see if we can get an example with some points in it. Okay, let's say something like that. Okay, right. So, okay, this, yes. Okay. So now I have, so let's say link 2 is this link. Let's say that's link 2. And so link 3, link 4 is this slider, link 5, link number 6 is this link here. That's 6. So I have 6 links. All right. So 2, 3, 4, 5, 6. So I mean, you can have many. You can find lots of points if you go 6, like n minus 1 over 2, and you can find yourself plenty of points, right? Maybe 15 points or something like that. But let's say I want to get as many as possible before, like, ending up with a messy drawing. So let's say I have here, I have, this will be point common between 2 and 3. This will be 2, 3. This will be 2, 5, this point here. Okay, this one here will be 1, 2. This point at the pivot will be, okay, the pivot will be 0.34. So this at the pivot here will be point, here will be 3, 4. How about 1, 4? 1, 4, of course, is perpendicular and to the sliding, and at infinity, this is 0.14. Okay, so we know 1, 4 is going in perpendicular to that. Okay, so at the other end, this point here is point number 5, 6, and this point is point number 1, 6. So, and now if you want to find any points, it's just matter of connecting, like looking for points with common numbers and try to see like the missing point. So, like for example, if I go, this is, okay, this is 2, 5, and this here is 1, 2. So 1, 5 would have to fall on this line. So that's, so the 1, 5 will have to fall on this line by way of example. So, right, so this will be locus for 1, 5. That's locus for 1, 5. So we'll keep this in the memory. If you want another locus for 1, 5, you say, okay, this is 1, 6, and this is 5, 6. So you can say, okay, now the common number is 6, the missing is 1, 5. So this will give you another locus for 1, 5. So you do that. That's another locus for 1, 5. 0.34. This here is 0.15. That's another locus for 1, 5. That's 1, 5. So you know 5 actually rotates instantaneously at this point in time. Not always about this point. This is the pole for 5. And you can tell that link number 5 does general motion. This link does general motion because both ends move. right? So normally when I have both ends move, it will do general motion. Like link number 2 does rotational motion because it has a fixed pivot. Link number 6, the pure rotation motion. Link number 4 is pure translation. But link number 5 does a complex form of motion which combines both translation and rotation. And those are the links with both ends move. Similar to this is link number 3 type thing. So if you want the velocity omega 3 for link number 3, it would be as simple as, for example, to do what? Just to extend, realize now that you have 2, 3 at this end, 1, 2, so you can extend this, both ends will give you a locus for 1, 3. This is locus for 1, 3, and this is this end here, this is 3, 4, and 1, 4 at infinity. So this will give you another locus for 1, 3. So you can tell that 1, 3 is going to fall on the intersection of these two lines. So this here, so 1, 3 will be over here. That's 1, 3. So this is the pivot of or really the pole of link number 3, which if I know omega 2 at this point in time, I can calculate omega 3 because 0.23 is common and I can get the velocity of this point with minimum effort. Just if I do that will be perpendicular to this line, which is equal to omega 2 R2 or omega 3 H3 if you want to call this whole distance H3 type thing. And then you can get your omega 3, and from omega 3 you can get the sliding velocity, and then you can move on to this other link, which is only a 4-body chain, right? So really this linkage connects a 4-body chain and a slider crank linkage. And we have shown before, like possibly I would have done a 4-body chain example for you earlier to find how to find the points. So I mean, you can keep solving this problem to find omega 5 if you wanted. If you, I can find omega 5 at this now, at this very moment, simply because I have 0.15. I have 1.5 here, and I have 2.5, and I know omega 2, right? So as simple as saying, okay, I know omega 2, so the velocity of this point, which is 0.25, is equal to omega 2 times this distance. I can call this distance L2. That's omega 2 L2, but it's also omega 5 L5, and I can say, so no, sorry, this is L2 should go only to the pivot of link number 2, and this is L5. This is L5. L2 is this side of the L2 this side of link number 2. This is L2, all right? So let's be clear on that because I need to go to the pivot. This is L2 over here. So this would give me omega 5 straight away, this equation. And then once I know omega 5, I can find omega 6 if I want to, because now this point, 0.56, is common between 5 and 6. So its velocity of this point is omega 5 times h5 if I decided to call this h5. It's also equal to omega 6 r6. And then I can get omega 6 from here. So from omega 2 I can get omega 5 from here, and then I can get omega 6 from here as well. And I can get omega 2 from here. I can get the sliding velocity from here. So just once you manage to find some points and you know what you're doing, you should be able to find as much information as possible. Okay, so now this is possibly the end of the velocity analysis. And in general, we looked at like how to do velocity analysis with equations using by differentiating the loop closure equation. And then I also wanted to give you this insight in terms of the velocity pole and in terms of the nature of motion in a plane, and the topic which links nicely into velocity analysis. All right. So thanks for that. And if you have any questions, please drop us a line on Moodle or by email. Good luck.